Hello, this video is about Newton's third law. Now, the version that most people have heard about is every reaction has an equal and opposite reaction. Now that can cause to a misunderstanding. This version here hopefully makes it a little more understandable. When two bodies interact, the forces they exert on each other are equal and opposite. So, I have a picture here of a gentleman pushing a wardrobe. Now, he pushes the wardrobe with a force of 50 newtons, and the wardrobe pushes back on his hands, through his hands, with a force of 50 newtons. So the wardrobe would feel 50 newtons, and the man would feel 50 newtons. Now, in this situation here, one would assume that either the wardrobe is, the whole situation is some constant velocity, or they are balanced and there is no acceleration. Well, this in fact is not true, because the forces are acting on different bodies. The 50 newtons pointing in that direction is acting on the man, and the 50 newtons acting in that direction is acting on the wardrobe. Now let's say that the floor on the wardrobe is the friction of the floor on the wardrobe is in fact 45 newtons. So you can clearly see here now that the wardrobe is going to feel a resultant force in that direction of 5 newtons and will therefore accelerate. So the resultant force on the wardrobe would be the resultant force is equal to 50 minus 45 is equal to 5 newtons. So it is not balanced and it will accelerate. Okay. Now the forces on the man, well, he's got 50 newtons acting that way, but acting on him from his feet pushing against the ground, to keep the consistency, I've calculated that he will feel a force acting on the floor, acting on him through his muscles pushing against there. He will feel a force of 57 newtons. Okay, and he will in fact be accelerating. So in fact the forces on him are not balanced, and the forces on the wardrobe are not balanced. However, the Newton pairs, when two bodies interact, the forces they exert on each other are equal and opposite, are those two 50 Newton forces acting there. Okay, now let's look at the law again in a bit more detail. So I'll rub this off. Now, so what about the forces? Well, these are if you break down what's happening to it. So these Newton's third law, the forces itself, they act on different bodies, equal in magnitude. They're equal in magnitude, these two forces. They are opposite in direction, and also they are the same type of force. Okay. In fact, they actually form what's known as Newton pairs these two forces. Okay. So acting on different bodies, and we've established that. So the man pushing the wardrobe, the force of the wardrobe pushes on the man, and the force of the man pushes on the wardrobe. So they're not balanced. They're equal in magnitude. Yes, they're both 50 newtons. They're opposite in direction. Correct. And finally, the same type of force. Now, there's two types of forces outside the atom. That is the force due to gravity, and what's known as the electromagnetic force, which is effectively contact force, or touch, or even where there's not contact between magnets. These are known as the electromagnetic forces. So it's gravity or electromagnetic, and clearly in this case they're both electromagnetic forces. So let's have a look at another example of Newton's third law. Well, let's say we got a book falling. To remove air resistance from this, let's say we have a book falling towards the moon. And that doesn't confuse you with air resistance. So here's the moon, and here is a book. Now, let's look at Newton's third law here. The book's weight, which is a mass times the gravitational field strength on the moon, we'll call that weight W, is one part of the Newton's pair. Now the equal and opposite force will in fact be the force on the moon of magnitude also W, let's move that W to there, pulling itself up towards the book. Now the moon is far more massive than the book, so consequently its acceleration towards the book will be very, very small. Okay. Well, however, the weight of the book compared to the mass of the book is such that the book will feel itself moving towards the moon greatly. The moon won't notice. However, they are Newton's pairs. They're equal and opposite forces, and they're the same type of force. They're both gravitational forces. Now, let's mix it up a bit. Imagine someone were to put a table just there. Now, this table doesn't change the fact that those are the two equal and opposite forces as the weight of the book. What it is introducing two new forces. There will be a contact force here, let's call that R, as a rarefaction force acting up there between the table and the book, and its equal and opposite force will be the contact, so that will be the table pushing on the book, and the book pushing on the table will be also R. Equal and opposite, same type of force, electromagnetic. Now this looks like a bit confusing, because often when we will say that the magnitude of the reaction force is equal to the weight, it is. The magnitude of R is equal to the magnitude of W, but they are not Newton's pairs. The Newton pairs are the weight of the book and pulling towards the moon, and the equal and opposite force of the moon being towards the book, and the contact force here between the table pushing on the book and the contact force of the book pushing on the table.